Hello and welcome back. Okay, just want to make sure you can hear me. Okay, today we're going to start talking about correlation. And now we use correlation in the word correlation in everyday language, right? And we know that it means relate when something correlates, right? It correlates. And today we're going to learn about the statistical meaning of correlation. So you're not ever allowed to use the word correlation from now on in the non-statistical sense in your writing, okay? Because you're going to know the statistics behind it. All right. Correlation analysis part 1. I have a little graphic there that we're going to talk about more very soon. Okay. So, what is a correlation? Here's what you do. You get scores are obtained on two variables for each individual, and then a correlation coefficient is calculated using the two variables. And we can think of them as variable x and variable y. And then we test the relationship between x and y across all the people who are in our study. So, for example, you might have Jack, Jill, and Dave, and so on. And Jack might have had a score of 7.5 on variable X or variable 1, and 4.9 on variable Y or variable 2. Jill might have scored 9.8 on the first variable, 3.2 on the second variable, so on. The main thing is that there are at least two variables, and each person has a score on each of those variables. Some questions that are not addressed by correlations are questions like, are Jack's scores and Jill's scores different? Hmm. Hmm. Are Jack's scores typical for most people? Are males and females or any other two groups scores different? Okay. We're only looking at whether X and Y tend to vary together in general across everyone in our sample. So with Jack scores and Jill scores, those are two individuals. Okay, that's not, we're not generalizing there. You can just look at them and say, yes, they scored different things, duh, because those are individuals. In terms of understanding if something is typical for most people, if we know what's typical, if we know the population mean and standard deviation, we can determine what's typical, and that's a z-score. And then males and females or any other two groups, comparing those scores, you know that you would use a t-test. Okay. So, which are questions we can use a correlation to address? Now, um, people think of things like, do children learn more from discovery learning or guided instruction? For that, I would do an experiment. And then I would do a t-test to see which group learned more, the kids who got the discovery learning or the kids who got the guided instruction. Is the amount of red meat I eat related to my risk of getting cancer? Now, this one could be good for correlation because you figure you can correlate, um, you know, people eat differing amounts of red meat and they may have differing risks of getting cancer. Um, and there's another way of looking at that. Well, another way of looking at that is that amount of red meat is continuous, and then whether you get cancer or not is dichotomous, right? And so there's a way to look at that statistically as well. Do males score higher on math tests than females? Again, with the two groups, I would do a t-test. Does life expectancy for countries vary as a function of per capita consumption of alcohol? Now, here we have, for each country, we would have two variables. We would have life expectancy, and so it might say 55 or 65 or 75 or 80, 85 or whatever the life expectancy is, and then the per capita consumption of alcohol. So, how much alcohol does each person on average consume. And so those two variables, yes, we could use correlation to address that. That's a very good example of what the correlation that you're going to learn about today, where you have two continuous variables and you're seeing if how one varies relates to how another varies. And then, do vegetarians have less heart disease than those who eat meat? That could be a correlation. It could be thought of as more of a natural experiment. Some people who are you comparing the meat eaters to the vegetarians, and then you're measuring their heart function, right? And that's two groups. We would do a t-test, right? But if you looked at it as, does the amount of meat a person eats relate to their heart function, then that would be a good use of a correlation, because heart function, you put a person on the treadmill and see how their heart does. And then you ask them, okay, how many hamburgers did you have this week? And so on. You could quantify their heart function as a continuous variable and quantify the amount of meat they ate in a week, let's say, as a continuous variable, and compare to see if there's a relationship between those two variables. Okay, you see where I'm heading with this? Okay, slide 5. So graphically, thinking about correlation, um, we have a few things when we have two variables. We have the mean of the first variable, the mean of x. We have the mean of the second variable, the mean of y. Okay? Then we also have this idea of a trend line. Okay? And some people think of a trend line as kind of like a moving average. Okay? Or I think how should my hand go with this image? Okay. Yes. I got to reverse everything. Okay, so there, that dashed line in this illustration is the trend line. Okay. Um, and it's also called a regression line. And in our regression lessons, you're going to learn why. Now, if we look at this trend line, the green line is the average of X. So let's go back to our heart function. Let's say that our hypothesis is that our null hypothesis is that eating meat does not relate to heart function. Our alternative hypothesis or research hypothesis is that eating more meat relates to heart function. Or let's say if the more meat you eat, the harder your heart is going to have to work. Okay? The more meat you eat, the harder your heart is going to have to work. So, the heart effort, let's create a variable called heart effort. Okay? And let's assume that these dots correspond to individual people's measurements of the amount of meat they eat and how hard their heart has to work to pump blood. Okay, so data point A is below the mean of X, or how much meat, and below the mean of Y, or how hard their heart has to work. So you see that? How data point A is it's below the purple line and it's to the left of the green line. Data point B is above the mean of X and above the mean of Y. And so you see that, how it's to the right of the green line and above the purple line. So data point A corresponds to someone who eats very little meat and their heart effort is low. Their heart doesn't have to work very hard. And then data point B is someone who eats lots of meat and their heart effort is high. Okay? Their heart has to work very high. And all the points are near this trend line that is drawn through the center of the graph. So we could say that X and Y vary or change together. They are strongly correlated. And another way this is shown is those two overlapping circles. Shared variability is what those are showing. Okay, they share a lot of the variability. So after you watch this lesson, if you click this link, it leads to the page where I made that little graphic, and it gives you a chance to explore correlation, and just look at some example data and see what happens with the correlation. Okay. So graphically, let's look at correlation graphically, and this, then we'll look at it algebraically, okay? So perfect positive correlation means that the exact, as one goes up, the other one also always goes up by the same amount. And that's how you get a straight line, okay? Perfect positive correlation. Um, so that is, when one thing is going up, so is the other thing. Okay? High positive correlation means you can see that there's a line there. There's definitely a strong trend. But the dots aren't making a perfect line. Okay, so it's a high positive correlation. Um, you can see a line, but it's not making a perfect line. And so in general, when one thing goes up, the other thing goes up. A low positive correlation is you can imagine that there is a line, but it varies. There's a lot of variability in terms of, for some people, when one goes up, the other really goes, is also really high, but others, it's not so much. And then for no correlation, you don't see any line. Okay, it's that like kind of scattershot image when you graph um, your first and your second variables. Low negative correlation, it looks like the line is going downhill. Yes. So, okay, the line is going down. Okay, and that means that as x goes up, y actually goes down. Okay. High negative correlation means you can kind of really see the line that as x gets higher, y is getting lower. Okay. As one variable is getting higher, the other variable tends to be lower. Okay. And then a perfect negative correlation means that things will change the same way for each participant. And so you get and you can, connect the dots basically and make a straight line. Okay, remember the formula for variance from a while ago? Let's look at things algebraically. You first learned about variance way back near the beginning of the course. Remember that? We can measure how much each data point varies from the mean, calculate each deviation, square it, sum the square deviations, and to divide by the sample size. And we get the variance. But what if we have two variables, right? We're talking about x and y. We're talking about amount of red meat and heart effort. Then we get what's called covariance. Okay, and then you have the distance not only from the mean of x, but also the mean of y. And you see that in our formula, the third formula for covariance, the second and third formula. Show the formula for covariance. Covariance is a statistic representing the degree to which two variables vary together. How much they covary. Makes sense? Okay. Remember that a positive times a positive is a positive, positive times a negative is a negative, a negative times a positive is a negative, a negative times a negative is a positive. If you don't remember, that's okay. Don't worry about it, because we're just trying to get get things conceptually here, all right? You are not going to have to do these calculations, okay? We're going to let SPSS take care of the calculations, all right? Um, when X is higher and Y is when when X is higher than its mean, Y also tends to be higher than its mean, then we have that positive correlation that we saw on the graph. Okay? When X is lower than its mean and Y also tends to be lower than its mean, then and Y also tends to be lower. Again, we have this positive correlation. When we got lower and lower, then we got this positive correlation. When one is higher, and the other tends to be lower, then we get a negative correlation. Where we don't have a pattern, we get no correlation. Okay? So when there's a pattern that's repeated again and again, we either get a series of positive numbers or a series of negative numbers. When there's no pattern, we tend to get zero. Okay, if you do the formula for covariance. The problem is that covariance isn't standardized, right? The distance from the mean depends on the units, right? So um, if we were to, let's take height and weight. I'm not I'm not that many inches from the average height for women. You can imagine that. Yeah, the standard deviation for height is, if measured in inches, is probably not that high, right? And if I'm within one standard deviation, it's not that many more inches, right? But when we're weighing in pounds, we'll have a decent sized standard deviation, right? And so it's much easier. It's much easier for me to be 10 pounds heavier than 10 inches taller, right? Being 10 pounds heavier than average is no problem for me. Being 10 inches taller than average would be quite unusual, right? And then I should, you know, really have played sports at some point. Um, so the standard deviation, the variance, the variability, um, the variance and the standard deviation, the variance is not standardized. It depends on the units, right? The standard deviation, we call it the standard deviation, but unless we're talking about it's standard error that's standardized. It's not standard deviation also isn't isn't standardized. Um, Covariance is not standardized. Okay, so uh, to to standardize to standardize effect size, for example, we divide it by a standard deviation. Remember how we got z-scores? We were standardizing um, a distance there by dividing by a standard deviation. To standardize covariance, we divide it by the product of the standard deviation of our first variable and our second variable. Now, Carl Pearson is who's credited with figuring this out, and he invented the most popular correlation statistic, or we call it the Pearson product moment correlation coefficient. In the 1890s, he was working with a professor named Weldon, who was a zoologist, and he was exploring the properties of the normal distribution among shrimp. And Pearson, uh, uh, used his math skills, applied them to shrimp, and we now have the correlation coefficient. Now, he wasn't working alone, it turns out. If you have the field book, in the chapter on correlation, there was they discuss a woman named Florence Nightingale David, I think was her last name, and not the Florence Nightingale who was the nurse, but this Florence Nightingale was a mathematician. Let's see, I thought I saved that page. Where did I lost that page. But anyway, her picture is in here. And I don't know if you saw Hidden Figures, but one of the exciting things to learn in that movie was that computers were originally people who did computations, and often it was women who did these mathematical computations. Um, um, Florence Nightingale David was Pearson's research assistant, and she's the one who did a lot of the work. She published the first table of correlation coefficients. Am I getting her last name right? Um, and so she did a lot of the work. She, of course, hasn't gotten a lot of the credit. In fact, I might have gotten her name wrong. Let's see. So did I get it? Let me see. See. I think I did get it wrong. Yes. But yes, in this textbook, the chapter on correlation is chapter 8. 6, 6, 9, 8. Here we go. I was right. Florence Nightingale David. Here's a picture of her. Okay? And she was the hidden figure behind Pearson's work. All right. All right. Slide 11. So, here was the formula that he invented to have a standardized way of looking at the relationship between two variables. We get a standard scale where the values range from -1 to 1, regardless of the original units, whether it was in inches or pounds, for example. And it can be used with continuous data. If we have an ordinal scale, so categorical ordinal, it's called something different, but the calculation is the same. And I think similarly for, hold on, let me see. Okay. And yeah, so there are different names for some same or very similar calculations that are all about correlation, but depend on the type of measurement, the data type. Okay, so here's an example. Ice cream sales. A student group sells ice cream each day at the end of a summer camp as a fundraiser. Do sales vary based on the weather? I'm going to guess that they probably do. And so we have the temperature, it's written in Celsius, and the amount of money the students make selling ice cream. So each of these would be different days. Our unit is how much ice cream is sold in a day. The covariance we would subtract from the mean for each of the variables. We would multiply the columns together and we would get a number there, and then we would divide by the product of the standard deviation. And we're not going to do any of that math ourselves. Um, um, wait. Divide by the sample size. Oh, yes, that's right. Because if you do some more math, then you can get to another um, another formula for standard deviation for correlation. Okay, but we're not going to derive that formula. um, um, but you can get basically what the covariance is, and in Excel it tells you how to there's actually a function where you can figure out the covariance, which you'll never have to do, hopefully. And then you divide by the two standard deviations, right? And that you can check your work in Excel with the Correl function. We're not going to use Excel for correlations, but now you know it's there. You could check your work with the Correl function. Okay. And what you learn if you did that is the the correlation is 0.96. Okay, so let me make sure I have this right in my head. Okay, yes. Here on slide 14 we were figuring out the covariance. How much do the two covary? The temperature and the amount spent. Covariance we're dividing by n minus 1, right? And then we take what we get from there and divide by the product of the two standard deviations, which is the correlation. All right. Okay. Now that got that straight. All right. But we can do it using Excel functions and we can do it in SPSS, which is where we'll be spending most of our time. How is correlation coefficient interpreted? If it's near 1, it means that someone with a high score on one variable is very likely to have a high score on the other. If it's near -1, someone with a high score on one variable is very likely to have a low score on the other. So there's negatively correlated. If it's near 0, it means that a score on one variable doesn't tell you anything about what a score on the other variable will be. So that's that high positive, high negative, and then no correlation. So for example, this is slide 17. Maybe this is made up data. Maybe the correlation between IQ and GPA is 0.95. It's not. Let's see, but maybe it is for some sample somewhere. That means that there's a high positive correlation or a strong correlation between, very strong correlation between IQ and GPA. It's close to 1, positive 1. But the correlation between IQ and weight, if R equals 0.13 and that line is kind of flat, see how that line is kind of flat? That flat line happens when there isn't really a relationship one way or the other. How about correlation between IQ and errors on an exam? If we were to graph that, we might see the line sliding down, right? Sliding down and meaning the higher the IQ, the fewer the errors. Okay, the higher the intelligence, the fewer the errors on the exam. Okay, so that would be like maybe a correlation of -0.89 or about -0.9. Okay, close to -1. And you see how on slide 19 you see and these other slides how it helps to actually have a like a graph with a trend line. A trend line could be helpful, but is often not 100% necessary in order to see to kind of visualize the correlation. And so with the correlation, we're looking at the direction of which way the line is going, but we're also looking at how close the dots are to the line. Okay, how much scatter there is, how much, yeah, or how close they are to the line, how strongly they're attached to the line. Okay, is that line strong or is it weak? Okay, important factors to look out for. Now, this is where correlation can go wrong. First of all, range restriction. If the correlation might either the correlation might not be the same for a smaller or bigger range. A small range may give a small correlation. You can't really see the pattern in a small range. So for example, if you're looking at shoe size and height, right? If you look at the first graph, it says at the bottom R equals 0.71. That's a strong positive correlation, right? And you can kind of see, you could probably draw a line through there, right? But if you were limiting it to people between the size of 8 and 9 inches, then it's hard to tell where that line would be going, what direction that line would be going. just because your data is limited. Also, also, um, it could vary depending on how like one part of a graph might look different than another part of a graph. And sometimes that happens when what you have is called a ceiling effect. I'm going to talk with you more about that a little bit later on. Another important factor is nonlinearity. This, like most of the, all of the, all of the, um, all of the statistics we're talking about in this course, there's an assumption that there's a linear relationship between two variables, that there's a straight line involved somewhere, not a curved line. Okay, all the math breaks down. If the line curves, big problems. Okay, if there's nonlinearity, the correlation it's supposed to measure the distance between a point and the best fitting straight line. But if the best fitting straight line doesn't match the data points well, there won't be the correlation will be low. There may still be a strong relationship between the two variables, but your correlation coefficient cannot identify that relationship. Also, a heterogeneous subsample. So, it could be that what looks like a strong correlation is just that there are two groups together. And the groups that, when they're separated, when they're alone, they have two different patterns. Like, and that can happen, for example, if you graphed height and weight for males and females. Um, you might, it looks like there's a really strong positive correlation, but you may not have that if you were only looking at one group versus the other. And finally, extreme observations. And this is probably the most common problem other than the nonlinearity problem, but we're going to deal with the nonlinearity by always graphing. Yes, always graphing, always doing those scatter plots to make sure we have a linear relationship. Extreme observations. If on the first day of ice cream sales, if I typoed the temperature as 142 instead of 14.2, the correlation changes from 0.96 to minus 0.38. Okay, so in that case, it's a typo, right? But sometimes there are actually real extreme observations, and they have a similar effect where they throw things off. Like that, for example, in this example, it changes the correlation from being positive to being negative. It changes from being strong to being more moderate. Okay. The right thing to do is to disclose the problem. Okay. To tell your reader what the correlation is like both with and without the extreme point. If you think it's a valid point, if it's not a valid point, I would not include it in my data set. It was an error. Explain why you think the extreme point may have happened. Okay, if it's a valid point. If it was just an error, I would try to solve the error when I realize that there's an error. Okay, and that's it for now. Okay, see you next time.